All right, welcome back. So today, our first lesson, for this week, we're going to be looking at the kinetic molecular theory, which is shorthand K.M.T, and we're going to be looking at law of combining volumes. Now, for kinetic molecular theory, I already have the answers put up here, so instead of just writing them out, I figured I'd type them and have them up so you can see them. So kinetic molecular theory, we're going to use to describe four things. So why gases are compressible, explain why they exert pressure, explain Boyle's law and Charles' law. So you guys will need to be familiar with these explanations as well. So first one, why gases are compressible. What we have right here is the distance between gas molecules is about 30 to 40 times the size of the molecule itself. So this means there's a lot of empty space for the molecules to get closer together when compressed. All right, so that's the first one. So as they're moving around, there's so much space in between them, you can actually force them closer together. Now, as for why gas exert pressure. So the force a gas molecule exerts when colliding with the surface of a container is related to the pressure, not pressure, pressure. That should be RE and not, sorry for the typo, should be RE and not ER. So what this means is the more collisions at higher speeds result in higher pressures because they're exerting more forces. So basically pressure results in how many collisions there are, and then of course the speed at which it's hitting the walls of the container that it's contained in. So we have Boyle's law. So you know that Boyle's law is P1V1 equals P2V2. So when we are using Boyle's law to describe, or kinetic molecular theory to describe Boyle's law, you have to relate pressure and volume. So how this works, that if the volume container is reduced, the gas molecules will collide more frequently with the walls of the container because there is less space and therefore will have an increase in pressure. All right. Then of course the opposite is the same. If we increase the volume of the container, the gas molecules will collide with the container less, and that will decrease the pressure. And finally, explain Charles' law. So remember, Charles' law is V1 over T1 is equal to V2 over T2. All right, so it relates volume and temperature. So we have right here an increase in temperature will cause the gas molecules to move faster and hit the wall's container more frequently and with more force. So this causes the container to expand, so the pressure can remain the same. All right, so we can't say the pressure will increase because this is under constant pressure conditions, right? That's why pressure isn't in the equation. So this is where the volume will actually adjust so the pressure stays the same. And there you go. So that is the using kinetic molecular theory to describe our four things: why gases are compressible, why they have pressure, explain Boyle's law, and Charles' law. So next we're just going to jump right into the law of combining volumes. So what this is that when measured at the same temperature and pressure, volumes of gaseous reagents and products of a chemical reaction are always in simple ratios of whole numbers. So we'll look at what that means now in a second. So we can only use this with gases that are produced or consumed, and it helps predict the volume of gases involved in a chemical reaction. So our first step is always writing out our complete balanced chemical reaction. So back, I guess, almost February now, or even January when we first started K.M.T, we looked at the 5 different types of chemical reactions. So these are going to come back again because we will need to be refamiliarized with them. So we're going to go through our first example here. So law of combining volumes is example 1. So we're going to consider this reaction of nitrogen plus oxygen produces dinitrogen tetroxide. Now we'll notice on the previous one it said that they always react in simple whole numbers, and these simple whole numbers come from our balanced chemical equation right here. So that's why when we balance we always have simple whole numbers so that we can have those. Now this mole ratio is basically from our coefficients. So if we look at comparing oxygen and dinitrogen tetroxide, we can tell that there's 2 oxygen molecules for every 1 dinitrogen tetroxide. So we have 2 moles of O2, remember ratio, for every 1 mole of N2O4. Now, You notice this ratio, we've kind of touched up on this again when we did conversion factors, that we have ratios to relate things. So this is where we're kind of going with this, that we're creating a ratio so we can convert two different units. Now for this one here where we have 2 moles, we can also even say or make that assumption that if these are under same temperature and pressure and everything like that, if we have same number of moles, then they're going to have the same volumes. So the volume, for example, we can, instead of saying moles, we can say there's probably liters, right? So there's 2 liters of O2 for every 1 liter of N2O4. Now, how this is going to work is that we can use these ratios that we just completed to solve practical problems. So for example, if 1 mole of N2O4 is produced, how many moles of oxygen was consumed? Well, if we write out our given, where we have 1 mole of N2O4. Now, if we use our conversion factor, or if we use our ratio that we just developed up here, same thing, remember we want our N2O4 to cancel out, and we want our oxygens to stay. So if we do this, we'll notice moles of N2O4 will cancel out, and we're left with 2 moles of O2. Right? And this could even jump forward, and in our next example there, using our liter ones. Right? So if 1 liter of N2O4 is produced, how many moles of oxygen was consumed? So same thing, we're going to use our liter ratio down here. We want to cancel out N2O4, so that goes on the denominator of our fraction or our conversion factor, and the unit that we want stays up on top. We'll notice that liters cancel out, N2O4 cancel out. What we're left with is 2 liters of O2, and that is our answer. Now, of course, these are just using the ratios that we have right there. This will get a little more useful once we start getting into things like this. So what if we have 2.5 liters of nitrogen is consumed? What volume of oxygen is consumed as well? So we're going to look back up here and figure out the ratio. So we have 1 nitrogen and we have 2 oxygen. So this is our conversion factor. Now, if we have 2.5 liters of N2, we are going to derive our conversion factor. So we want to cancel out our N2. So we have 1 N2 in the denominator, 2 O2 in the numerator. We will notice that nitrogens cancel out, and what we are left with is equal to 5.0 liters of oxygen is also consumed. So that's how so as you can tell, we need to have our balanced chemical equation first, and then we can apply that into any other example that we have. So our next one, this is more of a typical example that you guys are going to be expected to deal with, is that I don't give you the balanced chemical equation first, is you need to figure out what the chemical equation is and then use the laws of combining volume. So once you get your balanced chemical reaction. So in this right here, we have use the law of combining volumes to predict the volume of oxygen required for the complete combustion of 120.0 milliliters of butane gas from a lighter. Now normally, so I don't expect you to know butane, but butane is C4H10. Now, the reason why that's not given to you is, well, I know we're going to go over this example together. So first of all, we need to write out our balanced chemical equation first. So we got C4H10. Now, it is a combustion reaction, so it reacts with oxygen to produce CO2 and H2O. Now, we can use this, or a law of combining volumes, because everything here is gaseous. Now, in order to balance, remember for hydrocarbon combustions, we balance carbons first, so we have 4 carbons here. So we need a 4 in front of CO2. We got 10 hydrogens, so we go 5. Now, when we try to add this together, we got 4 times 2, which is 8, plus 5, that's 13 oxygens. So we know O2, 13 does not work, so we are going to have to multiply everything by 2, right? So this turns into 2, 8, 10, and 13. All right. So once we got that, now we're looking at oxygen and we're given butane. So we are going to write our conversion factor. So we have 2 butanes. That should be 10. That looks like an H. And that should also be 4. I don't know what I'm writing down there. C4H10. And we have 13 oxygen. So this is our ratio between butane and oxygen, and we're going to use this for our conversion factor. So we write down what we are given. 120.0 milliliters of butane. We are going to multiply by our conversion factor. So we want oxygen, so that means oxygen shows up in our numerator. We want to cancel out butane, so that shows up in the denominator of our conversion factor. So then this way, the units of butane cancel out, and when we apply this right here, we get an answer of 780 milliliters of oxygen. And that's how we apply the law of combining volumes to other examples. So start off with your balanced chemical equation, figure out the ratio, and then apply it. So there's a few more examples on the next page. Right, so we have water decomposing into its elements, and nitrogen and ammonia, which is going to be NH3, and ammonia decomposing. So we have 2 decomposition reactions. So you have to remember what those are. So pause the video and try those out. But I'm going to put the answers up in 3 seconds, along with their balanced chemical equations as well. All right, and here are the answers. So for example 3, we got 10 milliliters of hydrogen and we got 5 milliliters of oxygen. And finally, for example 4, the volume of nitrogen that forms, we have 150 milliliters. And of course, the workings right there. So make sure to pop out your CYU book and of course try some of these examples. And if you're ready, you can jump on and look at lesson number 5, which is going to be dealing with molar volumes of gases. All right, see you guys later.